Good morning, Amherst. Welcome to the final lesson for new material in this unit. Today we talk about LeChatlier's principle. Normally this time of year we'd be talking about playoff hockey. LeChatlier is one of the great names in science. You know, there are some great names. You know, Amadeo Avogadro. It's a great name, you know. Well, LeChatlier sounds like he should be playing defense for the Montreal Canadiens. Back to the point. Oh, what a blast from LeChatlier! What a shot from LeChatlier! Yeah, whatever. It's Friday. I'm feeling good. All right, so LeChatlier's principle talks about equilibrium and when you stress that equilibrium, and he came up with the idea that a system in equilibrium that is subjected to a stress will shift in the direction that relieves that stress. I think about now during COVID-19, we can all appreciate that. I've been locked up inside, I've been pretty stressed out. I'd like to get outside, move in the direction away from that stress. That's the whole notion of it. So when you affect one part of a system, while you affect the whole system. That's the deal. The whole system is always affected. You don't change the value of KEQ. Interestingly enough, temperature is the only thing that can change the value of K. Okay, so if your if your stress is temperature change, yes, you're going to change the value of K, but when you move in the direction away from a stress, you reestablish equilibrium. You get back to the same value of K. You just change the relatives values of all of the concentrations that are in the system. So the reaction rates are temporarily changed to reestablish the same value of K unless temperature changes. Alrighty, not so good, not so good. That's all right. So the three rules of thumb. You shift away from an increase. If the stress is like, hey, I've got some players in the game here and I throw in an extra one, well, I had the perfect amount. I was at equilibrium. I don't want any more. I've got to get away from that stuff. You want to use it up, shift away from an increase. Conversely, if you have the perfect amount of each of the players in the game, you take some away, well, you try to replace it. You shift toward a decrease. Pressure changes can only affect gases. That's kind of true for just about everything we've ever talked about. So if you have a system that has gases involved, well, we'll talk about that as one of our examples. If they're solids or liquids, pressure changes don't affect them. The particles are already touching each other. Temperature is not energy. Temperature is average kinetic energy. Temperature is not a form of energy, but if your stress does involve a change in temperature, think of the energy term in the equation as the temperature. It helps. They're not the same thing, but you can think of it that way. So, here are the examples. Basic system, A plus B in equilibrium with C and D. Pretty straightforward. What's your stress? Well, let's increase the concentration of A. I've got A and B and C and D in that system. I'm going to throw in some more A. So your stress looks something like this. I always put a squiggle down the equilibrium. I had A and B and C and D and they came to equilibrium. I put in more A. Your job is to get rid of that A. You shift away from an increase. Well, the way to do that, A is on the left. A is on the reactant side. If I want to get rid of A, I need to turn some A and B into C and D. I'm going to shift to the product side. So you shift to the right. When you shift to the right, you create more C and more D. You use up B as you use up the additional A. You try to get rid of the extra A you put in, so you shift away from that stress. Anything on the right-hand side of the equilibrium goes up. Anything on the left goes down. Now the net change for A, you might have thrown in, let's say, an extra 10 moles of A. Maybe you only used up 5 of them. So the net change still might be an increase, but it balanced it out. You used up a little bit more B, you created more C, you created more D, so that you get back to your value of K. So that's why I'll make this one a dotted line. It's a decrease, but the net change might be an increase. But in the end, C and D went up and B went down. Okay? Example number 2. Same system. In this case, let's decrease the concentration of B. Instead of increasing A, I'll take out some B. The system says, well, I had the perfect amount of B. I want that back. If you take some B out, you need to create more of it to replace it. So, you're going to shift to the reactant side, shift it to the left, which is going to increase A, trying to bring back B, and in the process you're using up C and D. Shift toward a decrease, the whole system is affected. C and D go down, A goes up. You might not have gotten back all of the B, but the change isn't as bad because after the relative concentrations are taken into account, you get back to the value of KEQ. There's your net change. Example number 3. Okay, now it's starting to look like chemistry. Haber process here. Nitrogen gas plus 3H2 gas, equilibrium 2NH3 gas, making ammonia out of thin air. So let's increase the pressure on the system. Think of, a big cylinder of gas, and you got your nitrogen, got your hydrogen, got your ammonia in there. All of a sudden, the bubble shrinks. That's going to increase the pressure. You say, well, if pressure goes up, the volume should go down. If pressure goes down, the volume should go up. Kind of conversely, we have this inverse relationship. We remember that from gas laws. If you remember, PV equals nRT. If this goes up, that goes down. They have an inverse relationship. So that's how you relieve the stress. You say, all right, so how do I do that? You look at the number of moles of gas on each side of the equation. So you say, all right, my stoic here is 1 N2, 3 H2s, 2 NH3. This is gas, this is gas, this is gas. I've got a total of 4 moles of gas on the left. I've got a total of 2 moles of gas on the right. So my pressure went up, so I want my volume to go down. That's going to relieve my stress. So shift to the smaller side. 2 moles occupy less volume than 4 moles. I'm going to shift to the right. That's going to increase ammonia. It's going to decrease hydrogen. It's going to decrease nitrogen. Once again, the whole system is affected. There's my equilibrium. There's my net result. Now you need to be careful with these pressure changing stresses because, look at example number 4 here. Nitrogen plus oxygen goes to 2NO. Okay, so it's a gas, it's a gas, it's a gas. I've got 1 mole of nitrogen, 1 mole of oxygen, and 2 moles of nitrogen 2 oxide. So let's decrease the pressure. All right. Well, I've got 2 moles of gas on the left. I've got 2 moles of gas on the right. No shift. There's no advantage to go anywhere. No shift, Sherlock. Oh, that's a pun. All right, number 5. X plus Y, equilibrium Z, and energy. Finally getting energy term into the equation. Okay, that's your kilojoules or your kcals. That's your delta H term right there. Let's increase the temperature of the system. Okay, well, temperature is not a form of energy, but I can think of energy in the equation as the temperature. I can think of it that way. You can adopt that model, even though it's, not quite true. It's okay, it works. A change in temperature means you are going to change the value of KEQ. That's the only factor that's going to change the value of KEQ. That'll show up on your practice test, by the way. That's a little something you should know there. Temperature is the only thing that can change the value of K. All right. Also, increasing your temperature, this is another huge factor. This shows up even on the Regents exam a lot. It's a kind of a misdirection. It's not a very fair question. If you increase your temperature, you're going to increase the rate of reaction. That goes back to kinetics. Both your forward and your reverse reaction rates are going to increase. Okay, but one's going to increase more than the other temporarily to reestablish equilibrium. And it's going to be a different equilibrium because you've changed K. So if you increase temperature, yes, the rate of the forward reaction rate increases and the rate of the reverse reaction rate increases. They both increase. However, your energy term here is on the right. It's a product. So it's not a form of, it's not heat, it's not a form of energy. But I can think of it that way. So if I increased energy, it's just like putting in more energy. Shift away from an increase, shift back to the right. You're going to increase the reverse reaction rate more than you're going to increase the forward reaction rate. So it's just like throwing in more of any of the entities in the system. You shift back toward the reactants, you get more X, you get more Y, you use up some Z, trying to get rid of that excess energy. Number 6, 1A gas plus 2B gas, equilibrium 3C gas plus 4D gas plus energy. Wow, it's a much bigger system here. Let's add a catalyst. Catalyst lowers the activation energy, both forward and reverse. Creates a new pathway in between reactants and products. It changes the reaction mechanism. It increases the reaction rates both forward and reverse. Equally. Once again, no shift, Sherlock. Catalysts do not change where equilibrium lies. They just get you to equilibrium faster. They change the rate of reaction, both forward and reverse, equally. Your homework. Worksheet 7, equilibrium, LeChatlier's. Now, they're going to ask you, like in this example, here's one of them. They ask you, here's a change, here's a change, here's a change. It's probably a good idea to rewrite these equations each time and do the whole circling, shifting thing like I did. It just seems to, make sense after you do that. But if you do it once and then you have to go back and redo it again, it helps if you rewrite that equation. So there are a dozen of these problems here. Okay, so this won't take that long. It's not a very extensive homework. However, we are coming to the conclusion of a rather large unit. So I will also post momentarily a homework that is due on Tuesday to be collected for a grade, Regents Review. Also called Worksheet 7, remarkably, because it came from the Regents curriculum. That's fine. This one is going to be due on Tuesday. And then due on Wednesday, a rather extensive self-test, a practice test. This bad boy, well, has 55 questions. I've created forms in Google Classroom, quiz forms for the Regents Review and for the practice test, and I will grade them all individually. Don't worry about the grades in there. I always do them all by hand and enter them into Aspen. And Wednesday at noon, the practice test will be due. We will do a group meet session to review it afterwards for questions, and then I will put up a test, which I will probably make due, I'm going to tentatively say it'll be due Friday, on thermodynamics, kinetics, and equilibrium. Lions, tigers, and bears. Up next, acids, bases, and salts, but we'll get there. All right, we're going to do a group meet session at noon today. Talk to you soon.